Don't tell him I said that.
Okay, welcome everyone to HO Colloquium today by Andres Munoz Zaramilo. It is my great pleasure to introduce Andres, although he doesn't need any introduction. Andres Munoz Zaramilo is originally from Colombia, where he did his undergrads in physics and electric engineering. He came to Montana State University for his PhD, which he finished in 2010. His focus was solar dynamo simulations. After his PhD, he did a postdoc at the Harvard Smithsonian CFA and a Jackie Fellowship. Then he became researcher for Georgia State University in 2013. His focus during his postdoc and GSU years was historic data restoration, including faculae, sunspot areas, and magnetograms, all focused towards understanding long-term solar variability. Since 2017, Andres joined Southwest Zurich, and his focus has been on different applications of artificial intelligence. This includes space weather forecast, instrument calibration, pattern finding, and pattern classification, integration of physics with AI models, and more recently, training and using foundation models. Today, Andres will be speaking on Introduction to Surya, a foundation model in heliophysics. Andres.
Thank you, Martin. Okay, so first, let me just tell you a little bit about how this project is organized and funded. So this was a commission. This project is a commission by the Office of the Chief Science Data Officer. So it is, not more like you do this for me kind of thing, rather than through the regular, proposal competition cycles. And this is an effort, it's a test of the concept of foundation models, the idea of these large artificial intelligence models that are multi-purpose. And the OCSDO has funded one for geophysics, one for heliophysics, one for planetary right now. So we're working on that. It's a very large team. It has a science core that I'm leading that includes people from 12 different institutions, covering a wide range of different aspects of heliophysics. And it has two engineering cores, one at NASA Marshall as part of the impact team, and at IBM. So the reason why this project came to be is as an experiment. And I think one of the things that I would like to leave this room with is that this experiment is an ongoing experiment. So it is not finished. We're not done yet. And the stage in which we are is a stage where we can use as much help as possible. One of the motivations is that we have a lot of data, but it's hard to replicate it. So it is hard to create mirrors, like for every institution to have a mirror of SDO. Every single piece of data that SDO has taken, to have it here in-house at HAO, to have it in-house at CU, to have it in-house at Surya, to have it in-house at Stanford, to have it in-house at the CFA. So it is hard, in spite of the fact that we have a lot of data, we tend to work with subsets of the data that is available. So we maybe get one image per day, one image per hour, or a full cadence, 12 seconds, but only 1 or 2 hours here, an active region there. So that's kind of like the way we're interacting with this. So the idea is, can we create models that help lessen that need for duplication? The second one is that if we want to use big data and big models, this is actually an expensive endeavor. So it is, it's out of reach of a lot of our community. And there is a lot of replication there. So the question is, if NASA, so if the agencies create models that are multi-purpose and can extend them to the community, this could be cost beneficial for the community as well. So this project, as I said, is an experiment to assess the viability and usefulness of agencies paying for the development of these complex AI models that can be reused.
Can I ask you a question?
Yeah.
So is Surya an acronym for something or just because the sun?
It's because of the sun. Yeah. There is a huge part of the team is Indian.
Oh,
And the geophysics one was named after, well, it's also named in Hindi, Prithvi. That's the geophysics one, means Earth. And so, there was a majority that voted for Surya. So anyway, this is this experiment, and it is, as I mentioned, it's ongoing. Now, personally, and this is something that we have kind of like assumed as part of our DNA, the DNA of this project, is that because we are assessing the viability of the viability and usefulness, and the answer can be is neither viable nor useful. One of the things that we're aiming to do is build this AI infrastructure. So use this, which is probably the biggest AI project in heliophysics to date, to create infrastructure that can be reused beyond the fact that you may or may not want to use Surya itself. So you could use it for other things. So building, and also an opportunity personally for me to upskill the community, people that have not worked with AI but would like to. Within the context of the Surya project, there is an opportunity to teach people how to frame problems from the point of view of an AI application that transcends whether this particular model and these particular weights are what is going to be used or not. So the take-home message, the thing that I would like you to take home as this. So the foundation models are, the definition of the foundation model is not super rigid. But from our point of view, the models are big and the amount of data that they were trained with is big. So that's like a necessary condition. And the third one is that a successful foundation model then can be applied to other tasks than those that they was trained for. Surya is a model that was pre-trained using data from the Solar Dynamics Observatory exclusively. We're using a transformer architecture, and I will talk a little bit more about that. And we have been validating it using a range of downstream applications. So the idea of the downstream is you have a task that you use to train your model, and then later you use that for other tasks. The tasks that you use to train is called the pretext task, and everything else is called a downstream application. Now, our preliminary results on what people call zero shot, so is without fine tuning or doing anything else to the model, shows that Surya is competitive when fine tuned for these downstream applications that we chose. And there is like this really, to me, compelling evidence that there is the ability for these models to kind of like learn physics in an empirical way. But we are finding that we don't have the same results when we use Solar Cycle 24, which is where we trained, and we validate on Solar Cycle 25, which we didn't include in our training. Now, as I mentioned, for us, the value of the development of of Surya and it's more that it goes beyond those weights. But the idea is also to build that shared infrastructure. And as I told you, this is an experiment that is not done yet. So the idea is that in 2025 and 2026 is the timeline where we will have a better understanding of where everything thresholds, the limits, the boundaries, and the capabilities of this model. So let's start with the definition of foundation models as models that are trained on vast data sets so that they can be applied to multiple purposes. So to me, the most powerful definition of what an AI model is a mathematical construct that allows you to approximate a function, a probability distribution, an operator. So it is something where you create the possibility of approximation. And, in the context, the most common context, you are working in what is called a supervised approach, which is you have a set of data that you want to connect with another set of data. There is a mathematical relationship that you want to establish. And that mathematical relationship, as I said, can be just a mapping. If I know this, from this information, can I get this? So it will be like a direct mapping. Or it could be also probabilistic. Given these conditions, what are the probabilities of me seeing this or that? Or sampling a probability distribution. If I say I want a picture of a cat painted in Picasso style, then I will randomly draw from a distribution a picture that looks just like a cat painted by Picasso. So those kinds of things. Now, the way we do this is by implementing models that transform the input into that output. And these models need to be built through, there are two things that they need to have. One is a learnable component. This is what enables the approximation. And the other one is it has to be built with operations that are differentiable. As long as those two things are true, then the approximation is possible. Now, the quality of the approximation depends on many things. It depends on whether there is a true relationship between your inputs and outputs. It depends on the capability of your model to approximate, so the complexity and versatility of this model. And also, it depends on what we have here, which is what is called the loss and optimization function, which is your ability of quantifying when the model is doing a good job, when the model is doing a bad job. So if you have input and output data, a set of mathematical operations with a learnable component that is differentiable, that will map one into the other, and a way of quantifying how good that approximation is, then you're in business and then you can use that. And ultimately, the way this is trained is by creating this multidimensional space where each one of your free parameters is one dimension, and you do a gradient descent optimization through that landscape. All possible because your model is built of differentiable operations that are nested on top of each other. So you can calculate gradients and take steps towards a better approximation of your problem. And all this is possible because of the chain rule and et cetera, et cetera. So when we are working in terms of supervised learning, basically the establishment of that connection between an input and an output, I find it useful to conceptualize it this way, where you have an input, you have your data input, you have an encoder that makes a mapping of your input data space into another mathematical space that we call latent or embedding space. And then you have a projection head that connects from that latent into your target space. Okay. This is useful because it breaks that box that was the differentiable model into components. And it turns out that there is a lot of the abstraction that happens when you can choose where to put your latent space, and you actually have a lot of control about what latent space, that intermediate space looks like. It could be physical, for example, if you want so, or it could have certain mathematical properties if you want them as well. But the idea is that, is what allows you to establish that connection. Now, historically, we did this called supervised training, where you had to have pairs. You had to know what input will produce what output. And that imposed a cost on the human aspect of this exercise, where the human was responsible for providing the machine with inputs and outputs that were known to be connected. Now, the idea of self-supervision solves some of this, in that you now work with your output data. It's actually your input data under certain transformations and conditions that are meaningful to your problem. So now your ability to establish labels doesn't require anything human effort. And so once you have established a proper pretext task, and I will talk about pretext tasks in a moment, then you create the potential for a training loop where the only limit is your computational resource. So there is a cost, and but there is not a human limitation anymore. Now, what people have found is that there are pretext tasks that are very effective for enabling the approximation or the creation of a representation of data that is useful and usable, right? And that once you train those, then you can fine-tune for many other things. So the idea is that you will retain the encoding of your pre-trained model, and then you keep those weights fixed, and you train only the projection. So if you're for a new task, and so, for example, in the context of large language, GPT is a pre-trained model. So GPT, I think it starts from generalized pre-trained transformer or something like this. And then that is a model that has been pre-trained to understand language. And then you fine-tune it to talk with humans. So the chat GPT is a fine-tuning exercise where you keep the encoding learned during the pretext task training, and then you only fine-tune with tens of thousands of human interactions where the human ticks. This was a good answer. This was a bad answer. I'm happy. I feel like I'm taking it seriously. It's treating me with respect. It's giving me the information that I need. And so you fine-tune it to talk, to have conversations. And so the idea is that fine-tuning requires a fraction of the amount of data that you use for pre-training. And so that's kind of like the appeal.
Just as a matter of interest, totally irrelevant to this discussion, but can you use it to train fake news? I suppose you can. And
Absolutely.
Is that what the Russians do with the? Is it similar to that, do you think?
Yeah, like you could, for example, say you can train the model to sound convincing.
Yes.
Right? So you can say, was this answer convincing? And the person will say yes or no. And it doesn't matter anymore if it's factual or not. And once you have those data that are annotated, you could train it for that.
So you can generate your own political universe, actually.
Absolutely.
Yeah.
Yes.
That's pretty scary.
It is.
I think we're living in it, actually.
Yeah. But not the majority of the uses are not going to be those. You can also train it to be like the most amazing dungeon master and take you through these journeys of fantasy and fun, this, or you can train it to be factual and troll the internet and give you a review of a topic, etc., etc. So, malicious uses are always a possibility, but they are neither the majority nor what most people would think, when given that power.
But I mean, for instance, the world we're used to living in until the development of this kind of thing had Darwinism to take care of those problems. So if something was not factual and you went out and said, it's okay to go and try and wrestle a bear and kill it and eat its meat, you come out of the gene pool. Is there an equivalent? Is there an equivalent actor that you could
I think that
deal with this Darwinistic?
I would say that at some level, yes. If you as I believe in
You could make some money at this, I mean, if you thought about, I think you should do that.
So can you go back to the previous slide just to bring it back to the science case?
Boring.
Yeah, well, a bit more boring than eating bears. But, essentially, another way to think of this is you've taken the entire 20 petabyte AIA input data set and reduced it down to a latent space, which is now 50,000.
yeah, that it would be like, let's say
50,000.
20 gigabytes or something like that of
Yeah.
weights.
Yeah.
Yeah.
So you only have to work with the latent space now, which is hopefully a good representation of the full data set.
Yes.
And you don't have to download 20 petabytes of data. You have to download 20 gigabytes of a latent space representation of AIA.
And the data that will support your application.
Yeah. Yeah. So if you want to do it for solar wind, you need all the solar wind stuff too, but that's the projection head side. That's
Yes.
your side.
Exactly. Okay. So now I'm going to talk to you a little bit about Surya itself. So our self-supervision setup is the following. So our input data are 4K by 4K stacks at a 12 minutes cadence. It's the full mission, although in the first release, we only use cycle 24. It has 8 AIA channels, the HMI vector magnetogram components, the 3 components, HMR Dopplerograms, and it also has the line of sight.
Good. Not a dot on there. I was going to comment that it's.
I forgot to put it there.
Okay, good.
Now, the architecture that we're using to abstract this or distill that knowledge is called the transformer. It's the visual transformer, and I'll talk about transformers in just a little bit, just in the next slide. The pretext task is auto-regression, so it's time advancement. So we give 2 stacks, one like the present and 1 hour ago, and the task is to forecast all these channels 1 hour into the future. So that's the pretext task. So auto-regression in language is like, I give you the first part or a sentence and you tell me the answer, or like twinkle, twinkle, little star.
Last word, last.
Yes, exactly.
Word next.
Next word, next word. That is the equivalent in auto-regression. So that is our pretext task. Now, we're working right now on another release, which uses a completely different pretext task that is called masked augmentation, when you remove pieces of information. So there will be the equivalent of having a sentence, removing some words and guessing what those words that you removed were. But the results, everything that I'm going to show you today is time advancement. And we're using the mean square error as our optimization function. Okay.
You can predict the stock market with this.
Yes, of course, people are trying to do this as well. Auto-regression for the stock market is like the perfect pretext task. Yes. Yeah. But that is like an interesting, those are like interesting, it's adjacent to space weather forecast, where you have a conditioning that is the present, and you're trying to guess something that you have not seen. And so in some sense, this is the equivalent too. So, all this kind of like explosion of capability that we have seen with large language models was made possible by the invention of an architecture called the transformer. So, prior to this, the architecture, and when we talk about AI, the architecture is the sequence of mathematical operations that you execute on your input that eventually lead to your output, right? And as I said, they are a sequence of mathematical operations that are differentiable but have a learnable component. So, if you look at a little bit in a simplistic way at the way we were doing architectures, the first architectures that were the simplest neural networks. It was called fully connected. Everything was related to every input, every output was related to every input in a way. And at every layer, every output was connected to any input. So it was very like, it was kind of like pretty coarse, But then people started realizing that there was an advantage to modifying architectures in a more intentional way. And so the convolutional neural network comes later, which kind of mimics a little bit the way we see, the way our vision works. So that's kind of interesting because it reduces the amount of weights that you require to process an image significantly by just saying, okay, an image is composed of structures, and all I need to do is learn filters that are a small kernel, a small set of weights, but that I convolved with the image to identify the presence of edges, of dots, of circles, or all these things. And so the idea of attention definitely comes from when we're talking about language. Language is very complex in that you have a set of words, and the words acquire meaning depending on its neighbors. Even like wind and wind can change completely the meaning just by the words that it has beside it. And the clue to the meaning can come from any of the words in the sentence. It's not necessarily the one that is adjacent or the one that is nearest, etc., etc. And meaning can have many different shapes and flavors. And so people came up with the idea of attention, which essentially is like a sequence of matrix multiplications where the whole matrix is learnable. And that basically connects all your inputs with all the pieces of your sentence, every word of your sentence in the matrix connected with every other possible word in the sentence creates that matrix that is learnable. And so they come in triplets, and there is like more to this. But ultimately, what the transformer created was a very effective architecture for attach meaning empirically to concepts that are they are defined by a unique, what people call token. Okay, so the idea is a little bit like this. So if you have France is my home, I speak fluent, and your task is autoregression, so you're going to guess what the next sentence is, right? And I'm going to guide you through this transformer architecture of a simple way. The first thing that you do is tokenize the sentence, right? So tokenization is that assigning a numerical code to every piece of data that is unique and repeatable. So whenever you have France, you have the same token. It's always the same token. France always has a single unique token. Is my home, every single one of them has a unique code, okay? Then you apply something that people have found to be very effective when building relationships between the inputs, the data. It's called positional embedding. And in some sense, it's kind of like a quantitative, a quantity attached to your data that tells where the position of the data is in the sentence, in the input sentence, right? But if you're working with things that are not words, you can imagine it also to exist, as a coordinating space, right? Then you have the multi-head attention. So these are the matrix multiplications that use the tokens and the positional encoding to establish learnable relationships between words. And so, there is no real easy way of showing this conceptually, but in some sense, the idea is that, if you're focusing on France, and the word France, and then you look at is my home, there is like France is my home. There is a relationship of ownership that exists in this sentence. But if you just focus only on France and home, there is a geographical relationship between these two words in the sentence. And if you connect France with speaking, then you have like a topical relationship with France that connects to the idea of language. So when you were working with language, this idea that there can be many different ways in which the words of a sentence are connected, and all these different ways of connecting is what allows us to give meaning to the sentence. That is what necessitated the creation of this multi-head attention. So when you now go beyond multi-head attention, you start creating these vectors. So now you start with a token, which is just France is a number. But after you have your first layer of attention, France goes from being a token to being a multidimensional vector. And the positions of that vector are not really easy for a human to understand, but they start building these kinds of relationships internally. Now, when we talk about the visual transformer, and this is the way Surya works, we're talking about breaking an image into blocks and assigning a token, building kind of like a visual language, a big visual lexicon. So when you have a visual transformer, part of the architecture is trying to come up with a number that is repeatable for a certain visual element and build on those tokenizations that are predictable and repeatable, like this is quiet sun, always, every time that I see this is kind of quiet sun. You can start building the other relationships and meanings across the attention layers, okay? So that is kind of like technically how Surya works. Then the question, and this is where Lika comes in and I come in and our science core comes in, right? So there is a very strong aspiration, technical aspiration in the exercise of Surya, right? And there, that has to be tempered at some level by physics as well, by heliophysics and what the problems that heliophysicists are interested on. And so, we went and looked at ADS to look at networks of citations. So, you can see these paper cites this other paper, this paper cites this other, and they cluster. And here you have for AIA and HMI during the SDO era, some of the keywords that define networks of citations. So you have space weather, there's obviously there, nanoflares, jets, short-term like stuff. In HMI, we have, transport, the meridional flow, tracking of features, pores, and et cetera, et cetera. And so what we wanted to see is, as we develop Surya, we wanted to bring kind of like scientists that belong to these networks of citations that don't belong to a single institution. So every single person is from a different institution across the United States. So even though this was a commission work, there was an effort to try to spread it geographically and topically across the community. And the other criteria that we used to choose our applications was reusability. So if we can create templates for using the pre-trained model easily by anyone, so choosing applications that kind of like create the entire end-to-end loop and are easy to modify by anyone with an adjacent problem, that's the other thing that we were thinking. So in terms of one-dimensional classification, we go from an image to a number, right? We were using flare forecasting, yes and no. We are doing one-dimensional regression, so we go from a stack of images into a vector. And we have that in the form of the forecast of solar wind at L1, the nowcast of the ultraviolet spectrum, and the K-index forecast at here there. In terms of 2 dimensions, we were doing image-to-image classification. So this is a segmentation problem. So if you have an image, this pixel, what does the membership of each pixel in the context of like types of solar structures? So is this an active region? Is this a coronal hole? So that's the downstream application that we're testing. In particular, we have focused on active region segmentation. Regression in 2 dimensions. So this is image to image translation. And these are our pretext tasks. Time advancement. So what does the future look like based on the present and the past? And active region forecasts, whether there is going to be a region on disk or not. And the last one was a 3-dimensional downstream application of coronal field extrapolation and perturbation of the magnetosphere. Now, these ones, of course, are the hardest ones. So it has been a challenge to implement them.
Your UV spectrum should be blue too.
Oh, yes, I guess. Yeah, when you do the regression, even though the usefulness of the UV spectrum is geoscience, I was locating them as how close they are to the source of SDO. And so EUV is still a solar.
It's right there.
Entity. Yeah, that's what I was thinking.
Photons travel.
I think the blue ones, of course, are the ones that push, there is a lot of things that happen between the sun and the earth that are not necessarily visible in SDO. And so I was highlighting those blue ones as those that, like, we know for a fact have incomplete information. And so,
Yeah.
Okay, so as I told you, there is a preliminary result that, so we did several of these ones. We don't have them all implemented yet. And the good news is that Surya is competitive when it's fine-tuned against our internal baselines. Now, we have not sat down to see if Surya is like outperforming anybody in the field or anything like that. But, based on our own prior work and our own internal baselines, and this is competitive, we choose one of the objectives. Now, there is this super compelling result that I was not expecting to get, which is kind of like a bittersweet thing, and I'm going to tell you a little bit about it regarding flare forecasting, which was, we were like blown away when we saw it and very sad when it turns out that it's not working in every case. But I think, to me, one of the things that's most interesting is that we have been extremely disciplined as how we separate, the data that we train, the data that we validate on, et cetera, et cetera. And I think that, with some work, this can be made to work for real, I think. And so first, let's start with the good. And the thing that I find very exciting is that, Impact, IBM, they want press releases and they get press releases, so we were looking for press release material. So the people at IBM said, hey, what would be really cool to show? And I said, well, maybe we can look at active region emergence. That's something that should be possible to get. He said, well, why don't we look at flares? And I said, there's no way we're going to do flares. But the people at IBM went and looked and they saw flares. Like, they saw this model forecasting flares, and so I was like, no, but this is a training set. Let's look at the test set. So I went and I looked at the test set. I gave them a list. They look, and the flares are there. And we're like, oh my God, this is crazy. And the IBM people were like, no, but we need to make sure. So they went, I looked at logs for file access, and they made sure that these files that we were looking at flares had not been accessed in months. Like, nobody in our team has ever accessed those files for reading or anything in months. And so what I'm going to be showing you is like not flare forecasting as we define it in the context of space weather, but more like flare evolution forecasting. So the flare is already underway. And then the morphology of the flare is what comes out of the model. So here is our first input. Remember that we do 1 hour, the next hour, and then forecast the hour in the future. And then we take our output and put it as input, and we chain them. This is called, we chain them so that it can forecast more than 1 hour into the future. So this is the first input. You can see an active region, this active region here. And this is the second input. So there is a little bit of rotation. Now here is the first output. So this is the first output, and now this is the ground truth. This is the real observation. So, we start here, second input, then the first output, then we put this feedback in, and we get the second output. And now, you get that flare ribbon, appearing in the right place in the image with a morphology. You can see some of the artifacts here of tokenization, the fact that we're working with little blocks, et cetera, this straight line and everything. But I was like, this is crazy. I cannot believe it. Except that.
So the left is the 1 hour ahead. And
This is 2 hours ahead.
2 hours ahead from the original, and the right is the ground truth.
The ground truth. Yeah. So 1 hour ahead is this one. And then we feed that hour back in and forecast again for another hour, and the flare is there. The thing that is kind of heartbreaking is that it didn't work for 25. So here is another sequence. So here is the first input, second input, first output, second output. So you can see here the flare is on the limb, and this is the ground truth. But when we look at solar cycle 25, you have first input, second input, first output, second output, but the flare is not visible. So you can see that here, there should be a flare, and the flare is not there for solar cycle 25. And so, this is something that we're trying to understand. I thought like, oh, I know, this is the polarity reversal. The polarity reversal is what is throwing this thing up. Is maybe learning that anti-hail regions are not as productive as hail regions. So let's just flip the images. But that didn't help. In fact, when we flip the image, 424, the flare disappears. So you have first image, second image, first output, second output, the flare is here. And if I flip the stack, you have first image, second image, first output, second output, and the flare is gone. So I think that this is one of the things where we had to kind of make assumptions. The idea that with solar cycle 24 will be sufficient to extrapolate into the future, but especially now, the rest of the sun seems to be doing what it needs to do, but it's just the flares that are super sensitive in this case, as far as we can tell.
This will show that I don't really understand what's going on, and that's fine, because I'm going to retire soon and I'll happily go fishing.
Bear hunting, I think.
But I would say, for instance, that the crucial aspect of a flare is slow storage and then build up and then release of energy in the same way that a thunderstorm will produce lightning, except electromagnetically instead of electrostatically. But the crucial thing about a flare, as we understand it, is that you have to have more or less real discontinuities in the magnetic field somewhere. And that's not differentiable.
Right.
So there's a class of solutions in MHD which are not accessible to what you're doing at all. And if a flare is represented, or at least some of the physics, even if there's an attractor trying to get you to that solution, I'm not sure that a sweet Parker layer, it's probably not sweet Parker, but whatever the hell it is going to be captured in anything that you got there by the algorithm or the data.
But the way I kind of like I'm taking this is that within the context of the full sun, right? The flare, what we see is the actual deposition of energy that becomes light, right? So what I feel the model is getting is the location of where that energy will be eventually deposited.
Could you do the same for a thunderstorm?
The equivalent for a thunderstorm will be, the equivalent for this with a thunderstorm will be when you already have the lining starting, right? Because this is 2 hours, this here is 2 hours into the flare. So this is the peak this timestamp is the flare peak. So this is 2 hours. Our input is 2 hours before, or 3 hours before maximum. So the flare is already underway. Maybe it's not like, this is not visible yet.
I see. So the flare was underway in your trainings data as well as it is here in the first couple of move slots. And now you're trying to predict what will happen in the future.
Exactly. So if you have lining and the lining already started,
Yes.
right?
Right.
Then what this will be predicting is the pathway of the lining.
Okay.
And so it's not fair forecasting in the operational space weather forecast of the sense of the.
Maybe it wasn't such a stupid question after all then.
No.
You tried
I'm gonna fly.
going 1 hour before that, like before, would the flare be still there if you start the rollout earlier?
Yeah.
Or like how much in advance? Like how far can you go before the flare until you don't get the flare signatures?
I have not checked that. 3 hours, 4 hours, 6 hours, I have not checked that.
Yeah, I mean, the interesting thing would be how far back do you go to predict that first, obviously flaring
Yes.
region on the left there. You've already got that started, and then it's learning, oh, now there's going to be a ribbon over here on the right. That's great, but we really want to know, when's it going to start? When's the whole thing going to
Yes. Now there is like I think, when I have been showing this, some people say, oh, I launch rockets. I would love to know if in the next 2 hours there's going to be a flare. So that's kind of like a niche that we can cater, if we
Those
can.
guys want to know 5 minutes. They need like they press launch, 5 minutes before the flare, hopefully. But 2 hours is good too. Yeah.
Yeah, except launching into thunderstorms to see if they do any better.
Okay.
Question.
Uh-huh.
So for cycle 24, you do this every single case. You get
It's there.
You can do different flares. You actually
Yes.
you do 2 hours before you would get the ribbon.
Yes. Yeah, I can show you this. I was going to show the statistics right now.
Yeah, they trained on 24. So
Yes, but this was not in the training set.
this specific,
Like none of the flares that we get that I'm showing you are in the training set, and our training set is padded from our test sets. These metrics that I'm showing you
yeah.
are padded from the training.
Yeah.
So
So I always wonder why people do this training on one giant block and testing on one sequential block later, when you could split the training set up into slices all through 24 and 25.
that's what we're doing.
Okay, good.
So our test set is a period of every year padded.
Yeah.
Right. So we have
Yeah.
2011, 12, 13, 14.
Yeah, good. That's
But yes, but here is the difference. So you can see these are the strongest 50 flares in our test set for cycle 24. This is the mean square error, and this is in a logarithmic unit, etc. But I just want you to focus on the difference in the distributions. So this is the flare is happening in this one, 2 steps into the future, and this is just 1 hour before that flare peak. So we're getting this mean square error of 0.2. And then when the flare happens, we get a little bit more error, but it's more or less the same. But when you look at cycle 25, you have, a bigger error during flaring times, but, a significantly more error during non-flaring times. And then if I flip the image, then this is, these are the errors that we get for 24. And these are the errors that we get for 25. So I think that, there was always a concern. We have a solar cycle worth of observations at an exquisite cadence, but the sun right now and the sun 20 minutes from now looks almost the same. And so, having a huge amount of data, there was always the concern, how much more is it bringing? And the concern is that if it is not bringing a lot, then we end up with a model that is very cycle specific. And that was always, something we didn't know, but now we do. A priori we didn't know, but so those are the kinds of things that we're working on this right now. So anyway, that's the ugly. But I think, there is from the point of view of reusing this, this was the dream, the holy grail. Imagine if I could have shown you that we were getting every single flare of solar cycle 24 and solar cycle 25, like that was like that, even the fact that we're getting them on 24 itself is unbelievable to me. Of course, we were all like so sad because it would have been such a result. But I think that what this is saying is that there is a merit to these models into solving some of those super hard things to forecast, like the morphology of the flare once it's underway, right? So we don't.
Let's explore this a little bit, and this is where you can add in the wisdom of your expertise. Is should there be any difference between flares in solar cycle 24 and 25? If you just think of a solar flare taking place in 24 and 25, do we expect there to be any difference in how it's formed, how it triggers, yes, there's the hail flip, but disregarding that, it should be the same phenomenon.
I'd be interested to hear what Scott McIntosh has to say to that.
Yeah.
Well, I mean, I
That's
think
the
that
discussion we need to
you
have.
can already see that even cycle 24 flipped. There is something fundamental that the model is latching on that is even hemispheric.
Yeah.
Because if we flip
Is the flip in north-south?
north-south, yeah.
No, the east-west.
North-east-west. Just north-south.
Did the magnetogram go into the training? Did the
Yes.
SMI? Oh, that went in there.
Yes.
Okay, so that polarity is flipped. So
Yes.
be some
But
that.
I mean, flipping it north-south should probably address that.
Oh, yeah.
Yeah.
I mean, you retrained it with the complete flips,
No, we have not retrained it.
but that would be kind of
It will be tilted
Yes.
opposite.
So I think,
flipping it, but also making it enter hail because MHD is invariant under science.
yes, so flipping it and flipping polarity. Yes, we didn't use augmentations in this training. So that's in the next release, we are definitely going to do augmentations.
Can I ask maybe a related question?
Yeah.
Could you go back to two slides? For the one on the limb, where you see the flare on the limb? Yeah, exactly.
This one?
Yeah, yeah, exactly.
Well,
And like,
that's
for
hard.
this, you essentially don't have magnetic information on the limb, right? You don't see much of the magnetic field there, but the model is still able to get the flare right. I mean, like, can you speculate how it gets this flare information there? Because like, there's also no signature before, right? Like, how is it able to predict the limb flare? There's no magnetic information.
But remember that this is not forecasting the flare, but the evolution of the flare.
Next word.
Yes. Next word. Exactly. So there is a flare already underway here. Maybe it's not clear because we're looking at logarithmic scales here, but the flare is already going on. This is 2 hours into the future.
So okay.
So the flare,
Yeah.
the flare takes more than 2 hours.
Mhm.
So there is dynamics going already that will imply the existence of the flare, even though it's at the limb.
We can say that, I'm just trying to process what he just said, that flares, when viewed on the limb, flares will develop in a similar way once started.
For example, I mean, you can imagine that there is not like, there is the flare should be in this area. Like this is a human can do. If I tell you there is a flare already underway in this active region, the human can say, oh, then I think it's going to be, a forecaster will be able to draw a circle that will likely include the whole flare, right? So this is not a task that humans cannot do. I think that we can do that experiment in which we actually ask people to draw the exact shape of the flare. And I think in that context, the performance of a model like this will be superhuman, but there is an aspect of it that is not superhuman. If you already know there is this active region is flaring, then you can draw where the flare is going to be. It's not going to be here. So there is a component to that makes this task not as, Now, I have not looked at this more hours into the future. I'm kind of like, that's something that is in my list to see when does the flare appear or disappear. That should be even for 24.
That would be really a good test, I think. I think the problem that you're focusing on flares is because the reason I think we're talking about flares now is that you have a cadence sufficient to look at the differences, but maybe we don't believe you would expect the thing to evolve. Flares are the only things that evolve in minutes timescales on the sun that we're aware of, aside from very small scale structures. So, for instance, you would expect your thing to work perfectly because there's not much evolution in, say, a coronal hole boundary or something like that.
Exactly.
So the reason you're focusing on it is because it's a relatively short time scale, right? But I don't think flares are really the target for this kind of work, are they?
It's true. It's true. And that is, I think,
Would be for me, it's a
I mean, yes and no. So,
forecasting element we lack.
And then
So-
TMEs, of course. I mean, it's the same sort.
yes. So these are, remember this, the context of these downstream applications that I was presenting,
Yeah.
when with our first release, we had this also tested. Flare forecast now in the next 24 hours, segmentation of active regions. So this is just there is an active region here or not. Solar wind forecast, ultraviolet spectrum nowcast. And these are all for which we are competitive with all our baselines. We outperform our own baselines, but let's say at the very least we can say with confidence that we're competitive. So the objective of being applicable to other problems has been accomplished, but this result is so tantalizing that has actually captured a lot of our imagination. So
Yeah, no,
that is definitely
it's
something.
fascinating. I mean,
Yeah.
I'm amazed it works at all, really. Well, not really, but
It's fascinating that it works at all in 24, and it's fascinating that it doesn't work in
Yeah.
20.
Yes, that's the other thing.
Sure.
so maybe
Yeah.
you need to.
There's no reason that you could think of that it shouldn't.
Yeah.
Well, like you said, the hail.
There are more things. There is instrument degradation. Maybe that is simply using it to cheat. I don't know. But that's kind of like what we're looking at. So
I was about to ask this. How do you correct for instrument degradation? If it's like
Two
it's the same as ET.
you use the auto,
No, we use I need to double check, but I think it's not the auto.
the AIA.
AIFI.
There might be still some offset there. It could be still that this regardless of the.
So we are at the end of the hour. I'm going to skip really quick to something. We're working on a second release, but we will hear about that later. I think one of the things that we are doing is we're creating these protocols for framing the AI exercise, and so that it's easy for people to follow it. So the pre-processing, fine-tuning, step-by-step guides, metrics that people can use for their own purpose that are auto-differentiable, ensembling and uncertainty, benchmarking, and an APJ overleaf template that is kind of like guides you through, define your splits this way, calculate the statistics, put them here, kind of like
Co-author automatically.
no, but I think that is something so that people that are coming in, like the people that have been the most interested in testing Surya are also the earlier career, and so it's kind of like and we're turning this. We're going to have a workshop in January, so if you are interested in potentially being part of that, there is going to be an informative component. It's at Southwest, so it's here in Boulder. So there is it's half a day of information if you're interested about that. But there is going to be, the rest of the week is going to be hands-on. So we'll be choosing 20 projects to fine-tune. So anything, if you're interested, let me know. And the idea is to turn that workshop, which is kind of like a handheld step-by-step from nothing to having the downstream, also into like a Coursera, like something where, like AI Helio, start with your baseline, do your splittings this way. Then, fine-tune, compare against your baseline, that kind of like step-by-step protocol. So anyway, thank you so much, you guys, for your time. I think those are the main things that I think, this is a really interesting project. And I understand that, some of the optics are not optimal because of this hunger for press release, et cetera, et cetera. But I will ask you not to discard it because of that. I think that there is a possibility for us to really build knowledge and take advantage of these technologies within our community. So, and I think that's more my job than it was that of the engineers that trained it. So,
Thank you. Questions? Okay.
Just out of curiosity, how big this effort was. Do you have an estimate how many GPU hours went into training the model?
yes, so these were 100, just for the pre-training, it was 128 A100s for a month. So,
Pretty small.
I can do that.
Yeah.
I can burn that easily with my model.
yeah.
So not too bad.
Not everyone has access to that though. Like I think people here have it, and through NAS maybe. That's I think. So you may have seen that Radiant has language for Surya. So that's also part of the reason why I have, I'm trying to spread the word, help in any way, so that if you're interested in pursuing a Radiant proposal using Surya, let me know. But one of the things that I think is really interesting that Lika has been working towards is that the whole Radiant is going to come already with a NAS allocation. So any Radiant project will have compute. You don't have to be part of HAO, but you are part of HAO. But not everybody has access to the HAO.
What would be like a minimum requirement for compute to run the foundation model, like for fine-tuning tasks?
So we have been able to fit it in 20 gigabytes of VRAM. But this is like, the smallest it has been.
Tom.
So it's trained on SDOML essentially.
No, well,
Processing of the,
a version like something like SDML, but full res.
yes, but my question is for the detector degradation, is it using that algorithm? Because that's
We're using AI.
okay, that I think is what's causing your 24-25 change. Because that algorithm to use polite language sucks.
What would you recommend? Is that
So
Is that better than stinks?
we in our LWS program trying to predict F10.7, we're trying to use AI images to predict F10.7. And we found that the degradation of the intensity over the time of the mission is so severe that our ML models really can't function well between distinguishing 25 and 24. So yes, Natasha Flyer came up with a better way of degradation correction using both F10.7 as a kind of a constant baseline that you correct back to, and the 94 channel did not degrade very much at all. So using 94 AIA and F10.7 as baselines to correct back to, we think we can do. We haven't done it yet, but we think that this is going to be much better than the current inversion of a factor that they're using based on sounding rocket flights that took place 6 years ago or haven't been processed yet.
yes.
So
And I think, Robert, you were saying auto calibration.
Yeah, I mean, like that work, like what they used was basically like random offsets and then train the model to predict like the degradation. Like, but they used like a clean data set and then applied like random shifts, and the model did a pretty good job. And especially like for the time period where there were sounding rockets available, to have like a proper calibration for this time, it was doing pretty good. And I think it's like
You know what I'm thinking? I'm wondering if that
I would
use friends.
like it was an FDL.
It was an FDL. But I'm thinking,
But yeah.
we could use that as an augmentation and see. For the other release where we're doing mask augmentation, as part of the pretext task, we could do auto calibration.
yeah, I mean, you've got to get beyond just the simple AI prep
Yes.
version because it's very poor, especially in 304. 304 is terrible.
Yes. And I think,
It's actually overcorrected. So cycle 25 is too bright after you correct using the AI prep compared to what it should be.
I it's really fun exercise you're doing. But I think there's something you might be able to turn some of these problems around. And for instance, ask the question, what would be the optimal data sets you would do if you had a decent enough model of understanding how the spectrum is formed? What I'm getting at is the information content of the data you're looking at is not very high.
I absolutely agree.
And
What's
yet
the
you've
next
got,
AI emission, right?
No, and that is something that we are actually also, for us is a problem, like for me personally, is a high priority problem, because let's say let's imagine a world where Surya is like the best possible foundation model that anybody can ever have. Then I say, I have the perfect model for you. All you have to do is fine tune it. And you say, great. So how many data points do I need to fine tune this thing? And I don't know. What are the optimal sets of data? Like, I think one of the things that we're now exploring with is how do we define sampling strategies for both pre-training, but also for fine-tuning? So if your problem is solar wind, what are, every single data point for solar wind, you don't need that for fine-tuning. So what is the subset of the Omni data that you should use for a solar wind fine-tuning application?
so that's what I really like, is because what you're doing is instead of saying, well, we've got these data and they're very interesting and they span a bunch of temperatures, you're asking, what question do I want to answer here before you start? And then you try and see if the information in your data, I mean, for instance, the kernels of those contribution functions are wickedly overlap.
Yeah.
So it's got a horrible conditioning number and all that stuff. And so just a plain inversion just wouldn't work. I mean, you have to regularize it, which means you have to throw information at it. So, and then also the HMI vector magnetic fields and the line of sight magnetic field. Sure, that's very interesting what it is, but you've got such a much higher signal to noise in the line of sight than you do in the tangential components. So except that the limb or something like this. So all this seems to be begging the question: what have I got to build in order to really understand? Say you had a problem like, I want to understand flux emergence on the sun. How would you go? What instrument and what data set would you use to do that?
And I think
that's the way. I would like to persuade the young people that that's the way forward here. We've had thousands of observations of EUV data. I mean, do we really need more? If you come up with a good reason, I think that's fine. But please come up with answering a
It's
question.
a really good point, because AIA was designed originally with sort of a human overlay of what temperature should we choose to sample the corona in a way that's kind of wide. But there wasn't a science question.
And it wasn't stupid. It was a good idea.
Yeah, and they did the best, for a 2005-ish thing. They chose a good set of wavelengths, but your point is well taken, that if you now take the standpoint of, I mean, I've been going to go one step further. I want to design the best foundational model of the sun. What inputs would I like? I think you'd probably said, I want more chromospheric data. I probably choose different coronal lines as my data set.
oh, I see. Like if I'm going to launch the next mission that will enable.
Do you need spectrum?
Yeah.
Imaging spectroscopy, or can you get away with broadband? Or
Yeah. And I think, those are things that, and I think, the Surya was a very basic, data sampling was had a very basic strategy. We are going to sample, we make sure our test is completely padded and isolated, but other than that, we'll use every point during cycle 24. Now, one of the things, to me, lessons that I think, is valuable, maybe you will think, oh, well, that was obvious, but with some of these exercises, starting with the simple sampling strategy is useful in that now there is a baseline and there is a clarity, So if we're going to sample what is going to be in the next iteration, our sampling strategy, we're now testing different sampling strategies, especially given that this is kind of like potentially transformative when it comes to flare evolution. So we're like kind of gearing a little bit that, but yeah.
But to use the ChatGPT analogy, ChatGPT was trained on the entire English language and other languages too, but the entire English language. Surya is trained on just sort of a subset of language of the sun. There's a lot of missing language in the data set that it's trained on, right? So how do you get that full
Yeah.
solar language to train a future foundational model on? And again, I think, chromosphere is obviously missing, but there's other things you could think of too.
And we have things in the pipeline that we were discussing downstairs, Cosmo, Gong, you name it. These are things that
Yeah.
you guys are going to be working with.
Outer coronal imaging
Yeah,
perhaps
yeah.
would be another one.
I think this even goes like into the direction of like a general criticism about foundation models for imaging data, because it's just so much data to process. And we see basically the success for language models, right? Like that's obvious. That's like really successful. But it's also like the amount of data that was used. And if you compare it like an image, if you would compare it like with one sentence, right? It's like not even close in terms of the data that we can like process like in an imaging foundation model. So that's really like one of the big points where people are asking, do we actually have enough compute power and enough data to actually train the model like this that can compete with a language model that just uses like very
But at the same time, the sun has a lot of, so if you want to do all natural images, like you have like, if you imagine all the images that you can make in 4K by 4K in color, RGB, right? That space is, gigantic. But now if you think about all the natural images that can fit in that 4K by 4K space, is a significantly smaller space than the original. That includes all the forms of noise you can imagine. But I think the sun as a the sun as something that has visual language, I think it's a particularly good example of something where you could potentially apply a visual language. I feel like the amount of self-similarity that the sun has is incredible.
It's always round. I mean,
No. Not only that, it's just like, if you look at quiet network,
yeah.
you can almost imagine that there is a subset of quiet networks that can reproduce any sun, any quiet network of any cycle of any form, right?
Yeah.
Because the quiet network is like salt and pepper, the majority is gray, those. So, and you have like these little patches, and those patches are actually kind of like blobby. So there is like this idea that you can have a very limited amount of quiet networks that will allow you to convincingly reproduce any quiet sun.
The embedding vector space could be essentially not too gigantic. Like
Exactly. The tokenization of the solar imagery can produce something that looks like the tokenization of a language. So how many tokens do we need? So
the embedding space is the key. Like the GPT embedding space is roughly 20,000 dimensional. So every token becomes a vector in a 20,000 dimensional vector space. And then they create, the generative part is creating, if this vector is here, I want something close to it, but they're working in 20,000 dimensions.
right. But
That may be enough for the sun, 20,000.
but that is in the context of the embedding is the meaning attached, but the tokenization is, a language has thousands of words.
Yeah.
And including composites or tie-ins, I think our tokenizers work with 15,000, 20,000 tokens for all language in the English language. So maybe there you can describe the sun with 20,000 tokens and produce any solar image with 20,000 tokens because of the fact that the governing equations are simple-ish. They fit a page or two or a book, a chapter or book. And so now, on top of that, you will add meaning, the 20,000 embedding dimension space that will attach to each one of those tokens the meaning that this is quiet sun, and you see it here, you see it reacts this, it has this free energy, etc., etc. So I do think that in the context of the visual transformer, the sun, I think, is a good application of the visual transform, potentially.
I mean, like I could, like maybe one argument here is kind of like, just to bring in the analogy to large language models, is kind of, if like, especially if you think about like the embedding space that you have and what you compress in, right? It's a good argument to say this is only the sun, right? And we only have the sun in there. But what makes ChatGPT, for example, like so successful is that it can do multiple tasks at once. So if you would say, for example, it can only do math and doesn't know anything about poetry, right? Would it be worse or would it be better in doing that? And I think there are a couple of studies that actually do comparisons of different performance in different disciplines. And the large language models that do the best in all disciplines are like basically the ones that have the broadest knowledge, like knowledge across everything. So apparently understanding how language works, for example, helps it to also like better solve math problems. And so on. It's not really related, but like having a narrow scope is apparently not an advantage of foundation model by itself.
Oh, I see what you mean.
Yeah.
Like potentially a visual transformer that it has the sun and the earth and the planets, and this will be even more successful than
Right.
one trained only on solar data.
It's similar for the language models, right? Because there are even like languages that have like a super tiny subset of like available language, like even languages that no one speaks anymore. And GPT learned those languages just from the small sample and knowing like language in general. So that's pretty fascinating. So something similar for the sun could be also like the case you see, but it's like a much more complex problem with the imaging data.
So that made me, again, I'm not sure I'm understanding the actual discussion there, but it made me think, what happens, and you must have done some tests with a lower resolution set of images.
Yeah.
So if you bin it down, at what point you start losing information because it's arbitrary what you got. The sun doesn't know about the pixel sizes that you're choosing.
We trained, so I was actually concerned that, how many tokens we have in the image are defined by the size of the tile. So right now, Surya is using a 16 by 16 tile, which is really small. It's like this little thing. And I was talking with the engineers and telling them, look, I'm concerned that there is not enough information in a single 16 by 16 tile, that we should use bigger tiles so there is more richness to the meaning of the tile. And at the same time, do we really need 4K by 4K? Because there is an advantage of being able to include more samples in memory. When you're training, you can train faster, you can go through your data more times. So working with 2K by 2K will multiply our batch size by a factor of 4. And so they did experiments with bigger token sizes, like tile sizes, and lower resolution. But what we were finding is that for the same pretext task, the model performed better with smaller tokens and with bigger images. So now we didn't do a full pre-training.
Does that argue against self-similarity? On any scale across the sun?
So the way I understand it,
Yes.
is that there are two places where there are two parts of the model that are learnable. One is the tokenization, so the creation of the visual language, and the other one is the attention, right? When you have bigger tiles, you require more tokens to describe the language, the visual language, because the smaller the tile, the smaller the number of unique tiles you can have, right? So there is a balance that you can go for a need for more tokens or more pressure into your attention. So when you have smaller tiles, you're forcing you're really putting a lot of cost into the establishment of relationship between tiles and less into the creation of the visual language. Now, in particular, the creation of our visual language was linear. And so it is possible with a nonlinear aspect. What I'm telling you the outcome could be different. But specifically for this architecture, what we found was that it was better to have a simpler visual language and a more complex mechanism of attention than vice versa. Now, when it comes to the actual size of the image, I feel that the answer is also related, right? So the idea that for a 1 hour, this of course is based on the idea of 2 hours, 1 hour into the future. So this may be different if you change your pretext task, but the dynamics of the sun at these time scales benefit, like when you're forecasting the future, it's beneficial to have the full resolution over the downscaled one. So that's kind of like how I'm interpreting these results. Of course, this is not like a true fully pre-trained model against a fully pre-trained model. It's how one model was performing after a couple of epochs. An epoch being the model having seen the entirety of your training data once. So, in the end, this model trained, I don't remember for how many epochs, but let's say less than between 50 and 100. And so just going with like 5% of the training time, you could see that full resolution smaller tokens was outperforming lower resolution bigger tokens or similar token size. And so that's what in the end I said, okay, you guys, let's go with the, but yeah.
So it's an algorithmic issue as opposed to a physics issue. And when I was arguing about self-similarity, I just naively thought that as you bend and bend and bend, you would get.
No, you're totally right. It is, I think you're totally on the money. So self-similarity simplifies the visual law vocabulary.
Okay.
When the token is smaller.
Yeah.
But the full resolution, given an architecture that is an approximation to the actual rotation and evolution of the sun, the full resolution image is more conducive given that architecture, that the ability of the model to approximate the future benefits from having the full resolution. That doesn't mean that there is no maybe another architecture that would produce models that outperform at a lower resolution, et cetera, et cetera. But for this particular architecture that we used, it was beneficial to have the 4K, and it was beneficial to have the small token size, the small tile size. Many tokens in an image, but very simple tokens, each one of them. Yeah. Okay. Thank you so much.
Speaker again.
That was the most interesting, enjoyable talk I've heard for a long time.
Oh, thank you. Thank you.
What it means,